I've called this lecture The Art of Rock Tunneling to try and differentiate it from the science of rock tunneling, about which you can read a great deal in the literature. The art means the things that we have to do in conjunction with science of tunnel design to ensure that the tunnels actually are constructed safely and work. There is a lot of art in tunneling, and hopefully we'll see this evolve as I go through the lecture. A definition of the art of tunneling might be this, that it is the recognition of the most probable failure modes for the rock conditions encountered and the selection of appropriate excavation sequences and support methods to maintain the tunnel profile. The tunnel profile is fixed by the function of the tunnel, so that if you have a highway tunnel for 2 lanes of traffic, it has to have certain dimensions, certain height, in order to accommodate the lane width, the services, the ventilation, the drainage, and so on. Or an underground powerhouse has to have certain dimensions in order to accommodate the machinery that goes into it. So you are fixed with the profile of a tunnel, and our job is to devise ways of excavating that tunnel to that profile and maintaining the profile, because any loss of the profile is a loss of efficiency, a loss of money, a loss of time. As an example, I've chosen probably the most complicated type of tunneling that we'd be involved in, or underground excavation, and this is an underground powerhouse, a conceptual sketch. I'm not going to go into the detail, but you should know that the water comes in from the top left, the head race tunnel, as it's called, goes through the turbines, and it comes out through the tail race tunnel and is discharged back into the river or reservoir. There are a number of excavation shapes and sizes in this type of construction, and as you see from the photographs on the right, you need to sequence very carefully the excavation. So you would start with a tunnel running right down the middle of the machine hall from which you would do your exploration and planning, and then you widen that out, carefully installing support as you go. And finally, in the bottom right is an almost completed cavern with the turbines being installed at the bottom, and an overhead crane which is installed early in the construction to help you get the equipment and to remove the rock. So there is more than just digging a hole and putting support into it in tunneling. There's a lot of activity that goes on to ensure that you achieve these goals of maintaining the profile. In order to determine what kind of problem you might encounter, I've constructed this matrix of 9 conditions. There are many more than that, and I have diagrams which are much larger than this, but this is about as simple as I could make it. And so starting the top left, you have very high quality rock, intact, low stress, and the tunneling is very simple. You don't need support, you don't need any special conditions, you just go ahead and mine. And then as you work your way down that column on the left, as the tunnel gets deeper and deeper, the stresses get higher and higher, and if you get down to 2 or 3 kilometers below surface, you can expect to get conditions where the rock will fail pretty catastrophically, and in the worst case, as what we call rock bursts. In the middle, the top center block in the matrix is controlled, and this is very close to surface, is controlled by the structural features. So the blocks literally drop out or slide out because there's not sufficient confinement to keep them in place. So that's a special case. And as the stresses become higher, as you go deeper down, the rock is more closely interlocked and much more stable. On the right-hand side, the column there, which I've called sheared rock, is rock that has been tectonically disturbed, generally in alpine environments or in the Himalayas in India, the Andes in South America, the Rockies in North America. These have been formed by huge movements of the crustal plates, and they have, in this movement, in the mountain formation process, severely deformed and in many cases broken the rock up into almost soil-like characteristics. And so that's a special category which obviously gets worse as you go deeper. So let's break this down into some simpler elements. And the first one is shown here as generally excellent tunneling conditions, or you might call it the sweet spot of tunneling. If you're lucky with your tunnel, you might get to work in these conditions occasionally, where you're either in very good intact rock or you're in jointed rock, but where the stresses are high enough to clamp it, but not high enough to break it. And so those are very good tunneling conditions. And then we come to this oddball right in the middle there of blocky rock at very low stresses. And you'll see in the sketch included there that you can have wedges or blocks either sliding or falling out of the rock mass, which you've exposed by your excavation of the tunnel. Looking at an example, this is from a project in Argentina many years ago, where you can see a wedge has fallen out of the roof of that tunnel. And so simplistically you would say, well, this is just a question of three-dimensional geometry. You can go in there and measure the discontinuities that have caused the failure and design a rock bolt pattern that has sufficient capacity to keep that block in place, and that's the answer. Unfortunately, it's not quite that simple, because the question then arises, and this particular tunnel was 12 meter in span, taken as a top heading and then benched down another 10 meters. So it was the tail race tunnel of a hydro scheme, and 12 meters span, 18 meters high. So we're looking at the top heading, the first 8 meters of excavation. And to go in there and install rock bolts is not as simple as it sounds when you say it. This is a photograph which might be a little bit difficult for you to interpret, but you can see a man in the middle of the photograph there drilling a hole for a rock bolt using what we call a jack leg, or a drill with a jack forcing it into the rock. And you don't need me to tell you that's a very dangerous operation. So that you come to ask yourself, can I really put people under an 8 meter wide span, fully open, and ask them to do that job? The answer is no, you can't. And so how do we overcome that? The answer is deceptively simple when you think it through, and it introduces the concept of pilot tunneling, which we use a lot in tunnel driving. So if you take your 8 meter span and you drive a tunnel 6 meters wide in the middle of it, 6 meters is wide enough that you can get your machinery in there and still do your job, but the wedge that you allow to form is now reduced from a wedge of 123 tons in weight to a wedge of 29 tons in weight. It's also much more tightly clamped because you've got a smaller span, not as much relief, and so it's pretty much guaranteed that that wedge would be stable and you can get in there and put the bolts in. But you put the bolts in for the final wedge you're expecting to occur when you open it out to 8 meters. So you do it effectively in 2 stages. You drive the pilot tunnel ahead, you support the rock over your overhead, and 10 meters behind, you drive the wings forward. So you're not impeding progress, the tunnel is still moving ahead at the same rate, but in 2 steps, with the pilot tunnel and then the wings. And this is a technique we'll see more and more of as I go through the lecture. Here's an example from a very shallow excavation of 18 meters span for an underground station cavern on the Oporto Metro in Portugal. So this is going to be a large station cavern, and it's only about 20 or 30 meters underground, and it's in weathered granite, so pretty much soil with loose boulders in it. Very difficult material to support, and if you get it wrong, you're going to drop the whole thing into the cavern, guaranteed. But what was done in this case is that the first step in the process was to drill, as you see on the left-hand side here, 12-meter long holes into the rock above the cavern you're going to create, and to flush the soil out of those with high-pressure water, and to fill them with grout, with cement or concrete. so that you are forming an umbrella of closely spaced holes of concrete, and a concrete arch over the face. Because not only do you have the roof trying to fall in, but the face is also coming towards you because it's unstable. So that protects the face, it enables you to get in then, and now you can do your pilot tunnel through that protected area, as you see on the right. So you see a machine working there, excavating the material, and installed behind it is a structure of typically lattice girders and shotcrete or shotcrete fiber reinforced, or some lining that is sufficiently strong to hold the excavation while you're creating the pilot tunnel. And then this wall is sacrificial, you remove that and you remove the rest of the tunnel. But you do it sequentially so that you are never allowing any area of the roof to be unsupported under which you're working. Moving now to the left-hand column of massive rock under increasing stress. The failure of this rock under increasing stress is really a function of tensile spalling. So as you'll see in a moment, the stresses, when they're high enough on the boundary that you've created by excavating the tunnel, exceed the tensile strength of the rock, and you get splinters or plates or slivers of rock forming, as you see on the lower right-hand photograph there. And these become increasingly violent and loud as the stresses increase. Here's an illustration of what I've just said, that if you calculate the stresses around that particular tunnel, the concentration of stress will occur at particular points on the boundary, and when that value there, which I've called sigma max, the maximum stress, exceeds about 45% of the uniaxial strength of the intact rock, tensile failure will occur. And that is demonstrated by the graph I've included on the upper right there. These measurements are from deformation measurements on specimens or measurements of acoustic emission from micro geophones that are attached to the rock. And you can see that igneous, sedimentary, and metamorphic rocks all follow the same pattern. Tensile failure starts at about 45% of the uniaxial strength of the rock. And then there's another graph down in the lower left there, which has the same ratio of maximum stress to uniaxial strength, and you'll see the failure starts there at about 40%, but it plots the depth of failure. And these are simple observations from the field, measurements that have been done in the real world. And you start off with very shallow spalling. The lower right-hand photograph there is of a shaft where there's minor spalling in the walls, as you see there, and just a small amount. And the top left-hand photograph shows that this spalling is fairly easy to contain with mesh and rock bolts. The one big feature of this spalling process is that once it happens and you don't allow it the rock to fall away, it's self-stabilizing. So you don't need to go back there and try and stop it. But you have to retain the profile. So you have to put something in there that will prevent the rock spalling out, because otherwise it will simply continue as each free surface is created. So we move on a little bit deeper underground now, and we get higher stresses, and now we're getting pretty serious failure of, let's say, the whole tunnel sidewall, as you can see in the bottom right-hand photograph. And this is much more difficult to deal with. In mining, where you are dealing with irregular openings which are the stresses are constantly being changed by mining adjacent areas, you have to try and prevent this rock from failing further. And that is typically done by this process of cable lacing, where you have rock bolts installed and mesh, as we have in the previous slide, during the early part of the mining, and you then lace cables over that by putting in more or less a very large hairpin into the rock, grouted in, and through that, the eye, you lace the cables to form a very tight and very strong mesh over the wire mesh that you've put on in the first place. This is very deformable. It allows the rock to breathe, as it were, but doesn't allow it to fall out. Brittle materials like concrete or shotcrete don't work in these circumstances because they are simply too stiff and they're too brittle. So they will not accommodate the movement. And finally, we come to the rock burst problem, where you're now very deep, you might be 2 or 3 kilometers underground, and where the rock is failing violently. And I'm going to illustrate this by an example from a tunnel in Peru called the Olmos Tunnel. It's located right up in the north of Peru, as you see in the slide here. It's a tunnel that goes through the Andes Mountains to take water from the wet area in the Andes to the dry coastal plains of Peru. And the tunnel is a total length of about 18 kilometers. The original, you see that in this illustration down here, the original few kilometers were mined under a Russian contract by drill and blast, and then that ended, and 13.8 kilometers were left to be mined by the company that did this. You'll notice also that this map on the left-hand side here, which is an accumulation of measurements and interpretations of in situ stresses around the world, that is maintained in Germany, called the World Stress Map. And the tunnel is being driven right across the Andes, parallel to the highest principal stress. So you can expect from the fact that it's 2 kilometers below surface at its maximum, that it's being driven across a major mountain chain with huge stresses across it, that there will be problems. Now, physically, you cannot measure those stresses before you get there. So you can't go down 2 kilometers and measure the stresses in the rock. That technology does not exist today. And so all you can say is, from our understanding, our knowledge of the behavior of rock under these conditions, we're going to have rock bursts there. And so the philosophy adopted by Odebrecht, the company that was given this project, was to not to try and predict or to prevent the rock bursts, but to deal with the consequences. The contract is interesting because it was awarded by the government of Peru to Odebrecht as a 20-year concession for design, build, own, operate. That means the contractor provides the financing, does the design, builds the tunnel, owns it, and operates it for 20 years. And their income is from the sale of the water that they transmit. After 20 years, they then hand it back to the government of Peru. So it's a very common type of contract, but a very good one for this type of project, because there's a very high incentive for the contractor to complete it so that he starts earning his return from the transmission of water. I'm going to show you a video now of rock bursting in the tunnel, just to give you a feel what this might look like. And the video lasts a couple of minutes, but you'll be able to see the effects of rock bursting. That's not the sort of place you would necessarily want to work, but in this particular project, it turned out to be safe. To my knowledge, there were no fatalities at all, no accidents during the driving of that 13.8 kilometers of tunnel. I have to explain to you the method they used to overcome or to deal with the consequences. And they decided right from the beginning that they would line the whole tunnel with steel sets, which are I-beams, steel I-beams, which are bent into a circular shape in this case, as you see there. So these are the steel sets. And they're attached to a concrete invert, the bottom layer, which goes in first, right along the base of the tunnel as it's mined. And that invert contains a drainage ditch in the center, as you see there, and the ties for rail lines. So as that invert is laid, and as the sets are attached to it, and the spacing between the sets is governed by the grippers of the tunnel boring machine, which hold the machine in place while it thrusts forward and cuts the rock. As the tunnel progresses, the rail line is laid, the water is drained, and so you have high-speed transportation to the face at all times, and you have drainage of the water out. And so as the tunnel progresses, those sets will take care of most of the minor popping and bursting that you saw in the video. Sometimes with a little bit of deformation of the sets or of the reinforcing above the sets, but safe enough for people to work in. And typically what they would do would be to stop for half an hour after the machine is pushed ahead. It does one cut of about 1.5 meters for every thrust of the cylinders, and then they stop and reposition. And they typically left half an hour after that stop for all of the afterbursting to take place and things to calm down before the crews went back. And this worked very well. They had one major rock burst, which is equivalent to a man-generated earthquake. So you can actually measure it on the Richter scale. And that was a very damaging effect. You can see that the steel sets were bent out of shape. The machine was quite severely damaged and required about 3 months to rebuild some of the components. But the important thing about this is that the steel sets are deformable. So in spite of the fact that this one in the foreground is bent right out of shape, it still has capacity to keep the damaged rock back. And so because they had high-speed transportation, they could bring their crews in almost immediately and start cleaning up, and they simply remove the damaged sets, replace them, and open the ground up. Because once, as I said earlier on, once a spore or a burst has occurred, the energy has been dissipated. It won't reoccur, except for a little bit of after activity behind the machine. But these are bursts that occur at or ahead of the face, and once the energy has been released, that's it. You're quite safe to go in there and do the repairs and repair the machine. And the tunnel was successfully completed and is now in operation, delivering water to the coastal plains of Peru. The tunnel, about 100 meters behind the machine with a steel set installation, shotcrete lining was applied. So that tunnel, as I say, is complete and in operation. The same philosophy was used in a tunneling project in China to bring water from the Yellow River to towns or cities in the Gobi Desert, which require water urgently when this project was set up. And they didn't have rock burst in that tunnel. The tunnel was relatively shallow, perhaps maximum depth of 400 or 500 meters, going through a variety of rocks. And what they did was they assessed the conditions along the 100 kilometers of tunnel that had to be built, and they decided that if they used machines with long telescopic shields, and they installed immediately behind them a shield concrete linings of the type illustrated here, they could go right through this at very high speed with minimal problems. And provided the design of the thickness and the strength of the concrete lining is adequate, that proved to be the case. And they achieved very high rates of advance in some of the tunnels. There were 4 machines operating simultaneously, and they achieved up to a kilometer a month in some of them. So they completed the 100 kilometers in about 2 years of excavation, which is very, very high advance rates. They did have problems. They occasionally got into a fault and the machine got stuck in the mud, as it were, and they had to stop and dig it out and repair it. But the overall progress was so high that a 2 or 3 week event of that kind really didn't damage their overall process of very high speed tunneling. So that's the art of tunneling. Coming to the other end, the really bad rock, which is in many cases very close to a soil in its characteristics, and where you see this kind of surface in the core where it's been sheared. These are called slickened sides, where the rock has moved and it's at very low strength. How do we deal with what happens in a tunnel here? Here's an example from a project in India, a hydroelectric project, a 27-kilometer long headrace tunnel to a hydro project. And in general, the tunneling was good, but they reached one area where there was a known very large fault. And as they approached the fault, the ground got worse and worse, so they started installing seal sets. And finally, they got into the fault proper, and they simply could not control it. You can see here the sets have been severely deformed. There's about a meter of displacement, and the tunnel is clearly unstable, not acceptable. A lot of work went into that to try and figure out what to do, and finally they brought in an Italian contractor and consultant to do a process called four-poling. And this is rather similar to the earlier example I showed you in Portugal, but in this case the rock is so bad and it's clay-rich, so you can't flush it easily. It's too sticky, and so what they do here is drill in pipes, basically 12 meters long and about 100 millimeters in diameter, and these are drilled right ahead of the tunnel to form an umbrella over the face, and the concrete is injected into the pipes so that they are grouted into place. In addition, you can, if necessary, use 12-meter long fiberglass rods which are grouted into the face ahead of the tunnel. Use fiberglass because you can cut it off easily, and it doesn't impede your progress. And behind those, under the protection of the umbrella, you then create your normal steel sets and shotcrete or concrete lining. This is a very expensive process. It puts the cost of tunneling up by a factor of 2 or 3 from normal tunneling, and it's only used in exceptional circumstances of this kind. But it is very effective. And there's a photograph of the four-poling machine drilling the four poles, and along the arch there's a step, and you can see yellow marks where the four poles are going to be installed, and they're close together and form more or less a continuous arch above the face to protect you. And they successfully work their way through a very large fault using this technique. Another project that is even more extreme is this one, which is in Venezuela. It's called the Yakima project, and it's a 25-kilometer long tunnel to take water again from a wet area through into a very fertile but very dry area near the city of Barquisimeto in Venezuela. The cover in this case is about 1,200, 1,300 meters, so it's quite deep, but the rock is extremely poor. It's close to a large number of major faults, and it's been distorted and deformed to the point where it has very low strength. The tunnel project was started in 1976, and it took them 33 years to mine all the way through. For a variety of reasons, there were problems, one of which was the selection of inappropriate tunnel shapes. The upper left photograph shows the deformed graphitic phyllite, which is the rock they were mining through, very weak and with very little residual interlocking structure. And the lower right is a photograph of a horseshoe-shaped tunnel that was chosen for some of the early excavations. A horseshoe is not a good shape because the rock tends to squeeze in all directions, and the first thing it will do is pop the floor up and break the connection between the walls and the floor, as you see there, and ultimately that leads to almost a complete collapse of the tunnel. This is many years after the tunnel had converged to this level, and they simply go back and remine it. But that's a very expensive and very time-consuming operation. So the question is, how do you deal with this from a design engineering point of view? This is an illustration showing how a tunnel deforms as it's mined through the ground. So the tunnel is coming towards me, shown by the red arrow, advancing out of the screen towards me. And as the tunnel moves forward, displacements start 1 or 2 tunnel diameters ahead of the tunnel in the rock. The rock starts to feel the tunnel coming. By the time the tunnel face arrives, about 1/3 of the final displacement has already taken place, and that's shown by this point here. And obviously the tunnel face is also bulging inwards, so that has to be thought about and dealt with. And about 2 tunnel diameters behind the face, you've reached the maximum displacement that occurs. Now, in good rock, these displacements might only be a millimeter or so, so you don't worry about them. In bad rock, such as this one, the maximum displacement here, could be 1 or 2 meters. In fact, the tunnel, in some cases, closed up altogether, disappeared and had to be remined. And so the way you deal with that is by installing support. But you have to be very careful when you put that support in, because you can calculate how much support you need to prevent further displacement. Once your support capacity and the lack of capacity in the rock has meet, the tunnel will be stable. So this plot here is of the support pressure from the rock ahead of the face. So imagine that the face is being supported by the rock in front of it. Behind it, you've created a cavity, but the face is still close enough that it's providing support. And as you move away from it, that support becomes less and less. So your deformation increases in this direction as you move away from the face. Now, if you put your support in too early, the danger is that the capacity will be exceeded. So if you put in, say, steel sets or shotcrete lining, it would have to be very heavy indeed, to accommodate the support pressure you need to stabilize the tunnel. How do you get a meter of concrete into an advancing tunnel? You can't. So what you do is you put the support in a rudimentary form of, let's say, steel sets, but you allow it to yield, and it is only activated when you are sure that its capacity will be adequate. So the blue line here is a yielding support system which kicks in perhaps 15 meters behind the face, and as it picks up the load, it reaches the intersection with the required support line and stabilizes the tunnel. The trick is, how do you allow it to yield? And it turns out to be very simple. You just put sliding joints in the steel sets. So the steel sets go in here, and they are shotcreted in place, but you leave a window of about 1 meter on either side. And in that window, you allow a 30 centimeter gap. In this case, it's a 5.2 meter tunnel. 30 centimeter gap on either side will allow it to close 0.2 of a meter. So you're allowing it to close from 5.2 meters, you over-excavate it down to 5 meters, and the joints simply slide until the ends butt together, and then the sets are locked up, and you complete the installation of shotcrete, and you put another layer in, and you end up with a tunnel which is now completely lined, in this case with 0.6 meters of shotcrete lining. And you might need to come back and put another lining inside that for long-term stability. That process from beginning to end to this point took 33 years. There's still a few years left. It's not in operation yet, while they figure out what additional lining has to be placed in there. So this hopefully has been a brief summary of some of the art that goes with the science of tunnel engineering, and that enables us to construct tunnels in what I think you will agree are some very, very difficult rock and stress conditions that we are increasingly encountering around the world. As the population of the world increases, we need more and more space, and more of our infrastructure is going underground. more and more trans-mountain tunnels are needed to bring water and oil and transportation and people from one place to another. And so these difficult tunnels are increasingly going to be our daily bread in the field of rock engineering.